So in this video, I'm going to walk us through a quick review of all the content you need to know before the final. So I'm not going to go into a huge amount of depth, but I'm just going to briefly sketch all of the different concepts, a few mistakes you should be wary of making in the final. And I'll be explaining the kind of basic rationale behind the more advanced methods of proof. So I recommend watching this video probably right before you do your start revision, so you have a sense of like what you ought to be doing before you start reviewing. But I guess you could also watch it right at the end just to make sure that you've covered everything. All right, so here's the roadmap. These are all of the different things we've learned in the second half of the semester, and I'll be walking us through each of these in order, one by one. All right, so we're going to start with rules of implication. Now, these are the first rules that you learned when we started talking about natural deduction. So here are all of those rules. Here we've got simplification, addition, conjunction, etc., all the way down to constructive dilemma, which I know for some people is the kind of most confusing rule, but maybe that's just because it doesn't come up as often. But I recommend everybody have a piece of paper with them where they write the name of each of the rules, and then they actually write what the rule is. And you can have this piece of paper next to you whenever you're doing natural deduction and in the exam as well. So this is kind of like a cheat sheet. And in a way, it means you don't have to remember the names of all of the different rules. But it shouldn't mean that you don't try to memorize each of the rules. So I really recommend everybody memorize these rules. The best way you can do that is have this piece of paper next to you when you're doing natural deduction proofs, and just do as many proofs as you possibly can. Because if you do that, even if you're not in a position at the end to always remember exactly what this rule over here, I'm not sure if you can see my cursor right now. If you're not in a position to remember that when you use the rule that says, okay, if you have two conditionals, you can infer the truth of a third conditional on that basis. Even if you're not always able to remember that that rule is called hypothetical syllogism, you can use your piece of paper to remind yourself the name of that rule. But the really important thing is that you're in a position to recognize when you're allowed to use that rule. So you need to be in a position to recognize when you have the materials on your piece of paper to use conjunction, to use modus tollens, to use disjunctive syllogism. Unless you're in that position, you're not going to be able to get 100% on the natural deduction part of the final. And that really requires that you remember each of these rules, even if you can't remember the technical name for it. That's what the cheat sheet is for. Okay, so those are the rules. I'm going to spend a couple of minutes now talking about the way rules of implication, okay, these rules, the way these rules are different from rules of replacement. So if you look at the first 2 points on the roadmap, first up we have rules of implication, and then we have rules of replacement. And these are two different categories of all of the rules you've learned so far fall into, and they have two features that make them different from each other. These two groups or these two categories are different from each other in just two different ways. So I'm just going to make those ways explicit, and in doing so, I hope I'm just reminding you of things that you already implicitly know. So it shouldn't be overwhelming. Okay, so the first one is that rules of implication, these ones apply to whole sentences only. So it might be helpful to have an example to know what I mean here. You might end up, right, at a point where you see something like this, okay? You see two premises like this. The first premise is a conjunction. The second is just an atomic sentence, Q. And you might think to yourself, you might notice that you have a Q here and you have if Q then G here, and you might think, oh, I can do modus ponens here. But super important, you can't do modus ponens on 1 and 2 here. Why? Because this conditional, if Q then G, is not a whole sentence. It's a component of a more complicated sentence. So on line 1, the conditional is just one conjunct. It's the right-hand conjunct of the conjunction, okay? It's a part of the conditional sentence P and if Q then G. So you can't do modus ponens yet. And that's a super important point. It's not true only of modus ponens, it's true of all of these rules, all of the rules of implication. They apply to whole sentences. And so if I wanted to do modus ponens here, perhaps because I needed to get G, I would first need to simplify line 1. I would get Q and G via simplification on line 1. And then I could do modus ponens on lines 2 and 3. Super important point. Okay. Second important point. These rules can only be applied in one direction. Now this, I hope, is going to seem like a super obvious feature of these rules, but because it's something that distinguishes rules of implication from rules of replacement, I'm just going to make it explicit here. Here I have modus ponens, okay? Modus ponens, this rule says that if you have a conditional and you have the antecedent of that conditional on its own on a line, then you can infer the consequent of the conditional, right? So this rule, if we want to follow this rule, we start with sentences like the two sentences that I've highlighted here. So we start with the conditional and the antecedent of the conditional, and we infer the consequent. We can't use modus ponens, what have I said here, to infer P, and we can't infer P and the conditional from Q. We can't go from the bottom, what we have on the bottom, something like Q, to a conditional and the antecedent of that conditional. Okay, that's not a good inference, and it's certainly not what modus ponens says. Okay, so rules of implication can't be used we can't go from the bottom to something like what we have on the top. So here's another super obvious example. If I have P and Q, I can simplify it, right, to get P. But I can't go, that's a good use of simplification, I can't go from P to P and Q via simplification. That is not a good inference at all, and it's certainly not the inference that we name simplification. Okay, I'm not going to belabor that point anymore because it should be fairly obvious. But as you'll see, this is a feature that makes rules of implication different from rules of replacement. So let's talk about those ones now. Here are the rules of replacement that you've learned so far. Super important to have those memorized. Again, write them all out on your cheat sheet. Super important to have these on your cheat sheet because rules of replacement, some of them anyway, at least on the page, look more complicated than rules of implication, especially, at least in my view, De Morgan's law and distribution and exploitation too. So have these on your piece of paper, just practice, 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 and then you'll know them off by heart, even if you have trouble remembering which one's called associativity and which one's called distribution, for instance. All right. First thing that makes these rules different from rules of implication is that these ones can be used on sentences that are parts of more complicated sentences. So here's an instance, right? Here's an example. So you might have this line, okay, we had this line on an earlier slide. You might notice that we have this conditional here, and you might want to do material implication on it. You can do that, even though this conditional is part of a more complicated sentence. That's okay. You can still do material implication on the part of the sentence. So you can turn line 1 into a conjunction of P and not P or Q via material implication. So this is a feature of rules of replacement that is just super different. Why can I do that? Well, let's look at the rule of material implication just to take one example. Ignore the text on the right here. Let's just look at this bit in the text box. Rules of replacement, what they're saying is, hey, what's on the top line here, the conditional, if P then Q, it means the same thing as what's on the bottom line, not P or Q. These two sentences are equivalent. They have the same meaning, so you can replace one with the other. And that means these rules can go in both directions. And so this brings me to like the second thing that makes rules of replacement super different from rules of implication. Given that this conditional, if P then Q, means exactly the same thing as not P or Q, you can substitute the disjunction on the bottom for the conditional and vice versa. So these rules, in a way, don't really have directions. You can go from the bottom to the top and the top to the bottom. They're not specifying inferences, right, that take us from one or two sentences to something else. They're just specifying that one sentence means exactly the same thing as another sentence. Think of rules of replacement as kind of like specifying entries in a dictionary. You might have a Spanish-English dictionary and you have gato and cat next to each other in the same entry. That entry says, hey, these two words mean the same thing. So you can substitute one for the other and vice versa. Okay. All right, so those are the two features of these rules, this set of rules that you would have learned. This was like the second bunch of rules that you would have learned when you were learning about natural deduction. And these ones have that feature. These two features, rather. They don't have a direction, and they can be used on components of more complicated sentences. Okay. Let's talk now about natural deduction notation and mistakes to watch out for. I've already done some examples of the notation, but it's worth, I suppose, making super clear everything that you need to be doing when you're doing these proofs on the exam. So here's an example of a really simple proof that I've completed for us. So this working out is showing that Q is entailed by these two premises. So this conditional and this conjunction entail Q. Now, what is this kind of like line here? What's actually like going on when we write the working out like this? Well, what we're saying is, I know that P is true. Okay, P is what I write here. I know that P is entailed by the premises because of simplification on line 2, because I can apply simplification on line 2. And if I apply simplification on line 2, I can infer that P is true. Okay, so that's just me explaining what's going on with the working out. Here are some things you really can't forget to do. Don't forget to number your lines correctly. Okay, so if your premises, if you have two premises, premise 1, premise 2, the first line in your working out should be called line 3, labeled line 3. So make sure you label your lines continuously, beginning with the line after the final premise. Okay. Remember to cite the rule you used. If you were completing this proof and you forgot to write what rule you used, like I've done there, you would lose some marks, you would lose some grades. Super important to actually cite what rule you used. If you're using abbreviations, like here I use MP for modus ponens, make sure it's unambiguous what rule you're referring to. Don't just like cite a rule, don't just say like M, okay? It's not clear to the person that's reading your proof whether you're talking about modus ponens, material implication, material equivalence. Super unclear. So make sure you abbreviate rules in a way that's super unambiguous. Final thing that you can't forget, you need to cite the line or lines on which you actually used the rule. Super important. People often forget this part, right? So you can't just write simplification, for instance. Oops. You can't just write simplification without actually specifying what line you simplified. Okay, so you have to write line 2. So 3 things. You need to make sure you've numbered your lines correctly. Okay, continuing on from the premises, you have to cite the rule that you used, and you have to cite what lines you used the rule on. Now, it's worth saying just a couple of things about this final point, okay? For some rules, you'll need to cite 1 line, but for others, you'll need to cite 2 or 3 lines. So if someone had done this proof, right, and they did modus ponens, and they wrote on line 1, they would lose some grades. Why? Because modus ponens is a rule that applies to 2 lines, so you have to cite 2 lines. Okay, so you have to have 2 lines written there. If you only cite 1, then that's a mistake. Simplification, on the other hand, is a rule that only applies to 1 line. So you only need to cite 1 line there. Okay, so here are the rules that apply to 2 lines, and so you need to cite 2 lines if you're ever writing down any of these as your justification. And constructive dilemma is the only rule that requires you to cite 3 lines. Two lines refer to 2 conditionals. The 3rd line cites a disjunction. Okay, so if you ever find yourself writing constructive dilemma out as your justification, ask yourself, okay, wait, have I definitely cited 3 lines? All right, those are kind of, in my view, the 2 mistakes people are most likely to make. Either not citing lines at all, or citing the wrong lines or not the right number of lines, or failing to actually justify their workings out, failing to actually name what rule they used. All right, let's go back to our roadmap. All right, I'm going to talk a little bit about indirect proof. I actually don't think I have a 6th section here. I think the mistakes to watch out for has just been incorporated into these 2 sections. So we're in the penultimate section here now. I'm going to start by just talking about the rationale behind indirect proof. Okay, so everything we've been doing so far, so this example and everything that I've just sort of been briefly sketching in the other slides, has all been kind of using the method of direct proof, right? This is the standard way we prove conclusions are entailed by premises when we're doing natural deduction. What's a direct proof? Well, we use the rules of implication and replacement to get the conclusion on a line of its own. And when we do that, we're showing directly that the conclusion is entailed by the premises. Okay, so when we just apply those rules straight to the premises and then try to get on a line of its own the conclusion, we're doing a direct proof. So what's an indirect proof? Here's a quick sketch of the rationale. what we want to do is show that if the conclusion is false, a contradiction would have to be true. But since we know from the first half of the course that a contradiction can't be true, the conclusion mustn't be false. Right? So we show a couple of things here. We show first that if the conclusion is false, a contradiction would have to be true. And then by showing that, what we've done is shown that the conclusion must not be false. It must be false that the conclusion is false. In other words, we've shown that the conclusion must be true. All right, I'm going to do one quick example just to refresh everyone's memory and make sure you're all watching out for the common kinds of mistakes. So here's a super easy proof, right? But I'm going to prove it using indirect proof. So I start off by, I put my conclusion over here so it's not in the way. I'm going to make an assumption. That's my first step. And the assumption, when you're using the method of indirect proof, is a negation of the conclusion. Okay, so my conclusion is Q. I'm going to assume a negation of the conclusion. So what I'm doing there is assuming that the conclusion is false. Okay, I'm assuming for the sake of the argument that the conclusion is false. And notice that when I make an assumption, I move everything over to the right. And that's a way of visually indicating that here I'm reasoning on the basis of an assumption. I'm engaging in hypothetical reasoning. All right. The second step is to apply the rules of implication, rules of replacement, as per usual, and I apply the rules to 1, 2, and 3, and I try to arrive at a contradiction. So here's an example of a contradiction, F and not F. The kind of sentence that, because of its logical form, it's just impossible for it to be true. So what I want to show is that if I assume that my conclusion is false, I would have to be committed to the truth of a sentence that is just impossible to be true. So now my goal is I make that assumption. I'm just trying to get a contradiction on my piece of paper. All right, so I'm just going to use these lines I'm just going to apply the rules that I know to these lines to see what I can get. So I'm just going to start by doing modus tollens on 1 and 3. I have not Q there. I have Q as my consequent. I can do modus tollens on 1 and 3 to get not P. All right, what else? Well, I can do simplification on line 2 to get P. And now I realize I'm pretty close to getting a contradiction. I just put not P and P together via conjunction. So conjunction on lines 4 and 5 gives me this contradiction, this sentence that, because of its logical form, just cannot be true. And so now on the piece of paper, what I have shown is that if the premises are true and the conclusion is false, a contradiction would have to be true. But that's impossible. It is impossible for a contradiction to be true. So if the premises are true, the assumption must be false. And so on the next line I write, I'm going to negate the assumption. Because once I get to line 6, I've shown that my assumption has to be false. So I write on the next line, on line 7, I negate the assumption, and my justification is indirect proof, and I cite the line at which I made the assumption and the line at which I the line at which I arrived at a contradiction, sorry. Let me just check what was written on this slide. Yeah, okay, good. I already said that. So this is a contradiction. At this point, we've shown that if the premises are true and the conclusion is false, then a contradiction would have to be true. Since a contradiction can't be true, and since we know that the premises have to be true, then it must be the case that the assumption is false. We write that down there, making it super explicit. And then we may as well do double negation. So let's go, just do, whoops, Q. Double negation on line 7, which is my conclusion. So whenever you get to the point where you're negating your assumption, you're basically at the point where you've shown that the conclusion is true. All right, let's see what I've written on this slide. Okay, this point is super important. When you're at the point where you're negating the assumption, this is the step after you found a contradiction. You need to return the working out to the left and justify it by, say, indirect proof. This is the point at which you are discharging your assumption. That's what it's called here. When I move my workings out back to the left, I am discharging my assumption. I'm showing that, okay, I'm no longer working on the basis of an assumption. I'm no longer engaging in purely hypothetical reasoning. At this point, I know for sure that if my premises are true, my assumption has to be false. And because I know that for sure, I don't just know it hypothetically, I know that it is the case that given the premises are true, this sentence here must be true. I move my working out back to the left. Okay, super, super important point. Okay, good, said that. Discharging your assumption. Okay, when you're doing an indirect proof, you always need to check that you've discharged your assumption. If you haven't, then you haven't completed the proof yet. Super important point. One of the most basic ways I can tell when people haven't learned how to do indirect proof yet is they make an assumption at some point in their natural deduction proof, but they never discharge the assumption. They might arrive at a line where they write down the conclusion, okay? But unless that's written down after you've already discharged your assumption, you actually haven't proven the conclusion yet. Super, super important. So let me make that a little bit more clear. Say we were doing this, okay? Say we were working out, we had a few lines in here. Who knows what they're going to say? We had a few more lines, right? Rather than just an 8-line proof, we had, 10 lines. And say at one of these lines, when you were reasoning on the basis of an assumption, you ended up with a Q here. All right? You had a Q, but it was in the working out that's indented to the right. You might look at that and think, oh, wow, I finished my proof. I've arrived at my conclusion. But you don't want to make that mistake. If you arrive at the Q and you haven't yet discharged your assumption, then you have not finished your proof. All you've shown is that Q is hypothetically true. Q is true if something that you don't know whether it's true, if this something else were true. You've shown that Q is true if you just added in a new premise, okay, which is kind of like what we do when we assume something. So don't be fooled by that. Unless you've already discharged your assumption, you haven't completed the proof if you find yourself writing down the same sentence that is the conclusion. All right. Oops. Now I've sort of messed up the order here. Good. Okay. One final point actually worth making. This contradiction can be made of anything. Here it's not P and P. You could have a contradiction that looks completely different, made of, I don't know, F and not F, or this is another contradiction, G and H, whoops, G and H, and not G and H. Okay, it's somewhat more complicated, but this is also a contradiction. So your contradiction could be made of anything, doesn't matter. What's important is that it's a sentence that just can't be true. And as such, you've shown that the assumption has to be false. All right. Conditional proof, and as I said, we're not going to actually have this final section, so we're in the home stretch here. First, I'm going to just briefly sketch the rationale behind conditional proof. It's important then to remember just a couple of pieces of technical language. We call the thing that comes before the arrow the antecedent, and the thing that comes after the arrow, the conditional, the consequent, okay? Super, super important. Here's the rationale behind a conditional proof. You can prove a conditional sentence, so a sentence like this one, if P then Q, by assuming the antecedent and then showing that if the antecedent is true, together with the premises, the consequent must also be true. So I assume, if I was proving this sentence using conditional proof, I would assume that P is true, and then I would show on the basis of that assumption that Q is true, and then I'd be finished. Then I would have proved using conditional proof if P then Q. All right, so here's an example again. I'm going to move my working out like that. I'm going to start by making an assumption. I'm going to assume the antecedent of the conditional I'm trying to prove. Okay, so G is my assumption. And now what I'm trying to get under the G, somewhere in my working out under to the right, I'm trying to get P alone. So the goal is to show that if G is true, then P is also true. Okay. I'm going to do disjunctive syllogism first on line 1 and 2 because I have this G here and I have not G or P and R. So P and R must be true. Disjunctive syllogism 1 and 2. Then I'm going to simplify line 3 to get P. And now in just 4 lines, I've shown that if G is true, okay, because on line 2, I'm literally saying, what would happen if G is true? Well, P and R would also be true, and P would be true. So I've shown at line 2, from line 2 to line 4, that if G is true, then P is true. And what I've said there is literally the conditional that is my conclusion. Oops. So I write down then, moving everything back to the left, if G then P, and my justification is conditional proof, starting on line 2, finishing on line 4, and I've finished. I've proved the conclusion via conditional proof. Now I moved my working out back to the left because at this point, I'm no longer reasoning on the basis of an assumption. I'm now discharging my assumption. I've shown that given premise 1, if G were true, then P would be true. So I'm no longer reasoning on the basis of an assumption when I say, well, if G is true, then P. That's a conditional that I know is true. All right. As before, super important point, when you're doing a conditional proof, you have to make sure you've discharged your assumption. So once you've finished it, look back at your working out, and if you haven't moved everything back to the left at some point, then you haven't completed the proof. Super, super important. You have to discharge your assumption. All right, final couple of points, right? You use conditional proof as a method to prove only conditional sentences, right? You literally assume the antecedent and then show that if the antecedent is true, given the premise is, the consequent is true. So you're proving a conditional sentence always. So it's awesome for situations like this, okay? The conclusion is a conditional sentence. You can totally just go straight, like use a conditional proof straight up, okay? But you can use it in other situations too, okay? You can use a conditional proof when it's part of a larger proof. So what do I mean by that? You should have done some examples like this already in the problem sets, but just as a reminder, if you have a conclusion that that's a disjunction like this, or any kind of disjunction, okay, you're able to use conditional proof as a part of a larger proof. So you could use conditional proof to prove if F, then G. Then you could do material implication on the conditional to get the disjunction. Because as we know, and I've already said it in this video, the conditional if F, then G is exactly the same as not F or G. So if we can do conditional proof to show if F, then G, then we're one step away, that step being material implication, from showing that our conclusion is true. Okay, so even though conditional proofs we can only use them to show that conditionals are true, that doesn't mean we can only use them when the conclusion of the argument we're trying to prove is a conditional. We can also use them when the conclusion of that argument is a disjunction, because disjunctions and conditionals are super closely related. We have this rule for transforming them, material implication. All right. Similarly, right, if you have a conclusion that's a biconditional, so here F, if and only if G, what we can do is we can do a conditional proof to show if F, then G. Then we can do another conditional proof to show if G, then F. Then we can join via conjunction those two conditionals, and then we can apply material equivalence to that conjunction. And I know that there's an example of a question just like this in one of the final problem sets, so I really recommend everyone go back and find that and practice it. But basically what this is saying is, hey, when you have a conclusion that's a biconditional, one method you always have available is conditional proof, but you have to do conditional proof twice to show that two different conditionals are true. Then you have to put them together. Then you have to use the rule of material equivalence. Maybe I'll write that fully out there. Material equivalence is going to turn that conjunction of two conditionals into a biconditional. All right. So at that point, let's look back on our roadmap. Got rules of implication, rules of replacement. Get to remembering those. Remember that they have a couple of slightly different features. Don't forget when you're writing up natural deduction proofs to cite your lines, to make sure you cite the justifications, cite the appropriate number of lines. When you're doing indirect proof and conditional proof, always when you make an assumption, move your working out to the right. Always make sure you've discharged your assumption. If you haven't discharged it, you haven't actually finished the proof. And remember that, I can get rid of this bit. Remember that conditional proof is used to prove a conditional sentence, but you can also use it as part of a bigger proof, especially when the conclusion is a disjunction or a biconditional. Indirect proof can be used on anything, right? All you have to do is negate the conclusion. All right, and that's it. Good luck, everybody.